Gauge, you mean the gauge, right? Gauge,
Yeah.
gauge boson. Gauge boson is part of the elements in the standard model. So do you want to, well, I can tell you two things. One thing is why they call this boson. Gauge is just a mathematical constraint, a condition, right? Every boson used in the standard model must be gauge, see? Gauge. Boson, right? Boson. Yeah. So this is idea. So basically you can neglect this just adjective, okay? It's just adjective. This is noun. So this is a key. This is keyword here. So this is a particle. This actually is not a single particle. Boson is a group of particles. You see. So first of all, the origin of this name come from the Bose. You know, the Bose is a India physicist. So that's his name. And the reason for the Bose because he both make a significant contribution to physics. So that's why we choose both. Another is fermion. Can you see? There are two type of the particle, two category of elements. One is the fermion, okay, and similarly, fermion come from the physicist. Is Italian American. It's called Fermi. Okay. That's how they name that's how they name these two type of the elements in standard model. Okay. So the difference. So we probably do some comparison. The difference, the boson is used to describe the there are more than one. So boson is to describe the interaction. So basically, this is used to describe the interaction between elements, between particle interaction. While the fermion is used to describe the matter, you see? So for example, atom and molecule, proton, neutron, electron. So these are two groups of this, basically the whole elements in the standard model can be divided into fermion and boson. Make sense now? Yeah. And another thing to be just probably a little bit abstract, it's called talk about a spin, right? You know, this particle, if you just imagine this particle is not a single, it's not a static, they will rotate. That is a property distribution. Can you see? Each particle can also spin or self-rotation. Can you see, like our Earth, right? So our Earth, so this Earth, this is the sun. Can you see? Our sun is much bigger. This is sun. So the Earth is a rotate about the sun. In the meantime, the Earth also rotate. It's called self-rotation. Can you see? Self-rotation. Rotation. So 24 hours a day, 24 hours a turn. Can you see? 24 hours, one day is one turn. Can you see? So you can this spin can be equivalent to the or comparable to the self-rotation. But of course, our particle is much smaller. So nobody care what does that really mean the spin is rotate. It's just a property. So spin is a property. Okay? So in terms of the spin, the fermion spin is always half. Okay. But for the boson, this could be 0, 1, 2, and so on. It's integer, you see. So that probably answer your question. So what is a boson? So this boson, and that is compared with fermion. Now the idea of the standard model is this. Okay, so what is the standard model? So that is basic idea. So the standard model, is called a standard model, which contain more than many elements. Okay, So standard model is that it say, well, our Earth, our universe, the nature is made by the particles, fermion, you see? And between these particles, they have interaction, can you see? Particle and particle have interaction. So this interaction is made by the boson. So this interaction, interaction, that is a hypothesis. So for example, if I just use the same coloring, so you can see the boson is a particle. You can imagine the particle can be exchanged like basketball, can you see? You can exchange between the two fermion, see? That is a little bit abstract, see? So the interaction is also described as a particle. Okay. So the question is how many interactions the standard model can describe? 1, 2, 3. They can only describe 3 basic interaction. One is electromagnetic. Okay. Another is called a strong nuclear. So that is a inside nuclear. Another is relatively weak. So the whole interaction in universe, apart from gravity, so there are 3 of them, okay? Now you may ask, so for each interaction, we must select the boson or gauge boson, right? For the for electromagnetic, we choose photon. You see, we use a photon. We use this notation. You know the photon, this Planck black radiation. They proposed the idea of photon. Yeah. For the strong interaction, we use a glue. Not glue, they call it gluon, you see. Actually, it's originally from glue. But for the correctness of English grammar, we have to remove this E, all right? So these come from the word glue. Okay. As you can see, in English, whenever we give a name for the particle, we often end with on, can you see? That is why when you if you check all of them, can you see? Because photon, can you see? Gluon, can you see? Boson, fermion, can you see? Electron, proton, neutron, can you see? Yeah. So that is how we name them. Third type of boson is called, it's just called W particle. Okay? W, positive and negative, and Z, the charge is 0, you see. 2 particles, 2 bosons are used to describe the weak interaction, okay? And the gluon is used to describe the strong interaction. Do you remember where the strong interaction, where does the strong interaction exist?
In the nucleus?
Nuclear, yes. Because we for example, when we study the nucleus of alpha particle, we have the alpha particle is made by 2 protons and 2 neutrons. See that? Now, without strong force, the Coulomb force is repulsive between the 2 electrons, between the proton. Can you see? That force would be too strong, so that we could never form the nucleus, because this pair of force are repulsive according to Coulomb's law. F, so this F is equal to a constant multiply E squared divided by R squared. So this R squared is so small. R is almost as small as 10 to the power of negative 15 meters. Okay, that I'm talking about the alpha or helium nuclei. You see. So that is why in history the strong force was introduced in order to explain the formation of stable nuclei. The strong force is strong or stronger then the Coulomb force in order to form this nuclei. Okay, if I draw the diagram here, you can see that. If I draw a diagram to show the strong force, this is just when you start a nuclear model. So for example, this is a distance between the two protons, right? And this is the diameter. This is diameter of protons. This is 10 to the power of -15 meters, right? So you can imagine that the force of the repulsive force should be very strong, you see, and so strong that it's impossible to stable for two protons stay together. So that force will getting weak as the distance increase. All right. I probably use different color because there is a stronger force. So I use this yellow color to indicate the Coulomb force. Can you see? The Coulomb force is getting very strong as distance increase. But unfortunately, these forces are repulsive. Can you see? Not attraction. So how can the nuclear helium nuclear stable? Well, that is a hypothesis. Okay, at the beginning, there is a force whose value is 0. Okay, but once the value reach to certain small numbers, they will just increase like that. Can you see? So that force is called, this is a hypothesis. So this is called a strong force. Now we can call it strong interaction, you see? At the beginning, we just call it force. But force and interaction are equivalent, it's the same thing. So this is a Coulomb force, can you see? Coulomb force. Now, as I say, in the standard model, everything, including interaction, are described by particles, right? Matters are made by fermion. Interaction are described by boson. Okay, so you can imagine that that is why I think that is all about this the question. You see, initiate your first question. This will give you a proper answer now. You see. Any other question associated with this idea on this page? You may ask, where is the gravity? Did you ask any students raise this question of gravity?
It says to describe the strong nuclear, weak nuclear, and electromagnetic forces in terms of the gauge bosons.
Gauge. Yeah, gauge. Yeah, gauge boson. Well, as I say, you can just say bosons. Okay, gauge is as I say, gauge is mathematical constraint for the for the mathematical formula for boson or notation for boson. All right, but it's just boson. Okay, well, perhaps I can ask a question. When we start a strong interaction, what are the gauge boson which boson is used to describe the strong interaction in nuclei? From this table, from this
interaction is gluon.
Yeah, the particle, the boson is called the gluon. Yeah. So you have the perhaps we put the adjective here. So the standard model is a standard particle model. See, everything is a particle. You see, everything is a particle, including the interaction. That is a little bit abstract. Okay. Because when we start chemistry, we know that particle model is okay, right? For example, you have water, can you see? We got water, and we know that is hydrogen. This is oxygen, you see? So we know it's a 3 particle, right? But when we describe the chemical bond, we didn't say anything, can you see? We say, well, this is a covalence bond. Do you remember? Okay. However, in the standard model, if you have the 2 quarks, another thing is quark, up quark and a down quark, all right? This thing between them, they must have interaction, can you see? this interaction is described by gluon. Can you see? I think they have used different in the Feynman diagram. Do you have you studied Feynman diagram?
Not yet.
Not yet.
But
yeah.
we will study them.
Yeah, so basically you can imagine that these quark, these two quarks, the up quark and down quark, the particle, can you see? This is a fermion. Oh, by the way, quark are fermion, can you see? There are two types of fermion. So one is quark. How about another one? Another called lepton. Have you studied lepton? Electron is one of leptons. Anyway,
yeah.
So unlike chemistry, in standard model, we say, well, there must be something in between moved. This particle, can you see? This particle is called gluon. So what happens is that these two particles exchange this particle, just like two basketball players. They exchange the basketball, right? So that they can feel that interaction. So this is something very abstract, can you see? In chemistry, we just simply call the chemical bond. Actually, we can describe the chemical bond by using Coulomb's interaction, right? Coulomb's law. Or sometimes we have used for the ionic bond, we can use a Coulomb force, right? Any question before we go?
What about electromagnetic forces in terms of?
Yes, good question. So electromagnetic force, let's just go to this one. So how to describe, so there are two descriptions, okay? So how to describe electromagnetic interaction, okay? That is the electron between charged particle, okay? Interaction. Oops. So there are two types of descriptions. So one is the Kanaska is used Coulomb's law, okay? Coulomb's law. Or force, can you see the Coulomb force? We use a force. That is a force can be written as a constant multiplied by 2 charge divided by the distance between them, okay? Now, for example, if you have 2 electrons, can you see? If you have charge, you have 2 electrons coming, can you see? So if the electron moves to that way, so if the electron moves this way, another electron moves this way, can you see? So if the electron moves that way, so the interaction between them will be built up, can you see? Repulsive, do you agree? It's repulsive between the 2 electrons, can you see? And that force will increase if this distance decrease. So that is the distance between them, can you see? So as a result, this is velocity. That's velocity 1, velocity 2. So as a result, what would happen? These 2 electrons will move like, so you see, can you move the trajectory? They will move like this. They will not collide, can you see? You can call this collide, but they just move to the closest distance and then change direction. Can you see? So that the force will increase at this stage. Force is the strongest at this position. Can you see? So this dashed line will be the trajectory of electron. Can you see?
Yeah.
So afterwards, electron will change direction. Can you see? And there's no additional term here. So basically, you can see if we want to edit the force at this position, the force is the strongest. At when the electron getting very close, the repulsive force is strongest. All right.
Mm-hmm.
So that is a description by use of Coulomb's law. Right. Now I suppose they tell you something. Now in the standard model, so in the standard model, how do we describe that? That is a standard model description. The standard model is different. Standard model. When we use the standard model, we know that this interaction would be boson. The gauge boson is a photon, right? So what happened? Can we just describe the same scenario, okay? And because we have used a photon, therefore there is no force anymore. All right, we cannot draw force. So therefore, if two electrons move like this, they will just encounter at a certain time. Can you see? Let's just use the arrow here. So I'm going to introduce the idea of the Feynman diagram. See, so you can see that when there's no force unless the time they exchange something. You see. So this I'm using the Feynman diagram now. So you are going to learn what is a Feynman diagram. Feynman diagram. So the two electrons, okay, when they move in this direction, at a certain point, they will exchange the photon. You see, very abstract. You can when you see this notation, you know that these electrons will exchange, like they hold their ball until they move very close. They change the ball, so both of them will feel the repulsive force and will move away. Can you see? And again, so this is the final stage. So electron is moving to that direction. So therefore, we don't have to draw the accurate trajectory. We just use a straight line now. Can you see? We use a straight line to describe the path of two electrons. So it's two electrons. Can you see the difference between these two descriptions?
Yeah.
In the first place, the Coulomb force is just the field. Can you see? There's no particle. Can you see? No boson. Okay? No boson. Can you see? Okay. In this description, and what is boson here? In this case, boson is, let's rewrite that. In this case, boson is photon. Can you see? Boson is photon. Why is photon? How do we know this boson is a photon in this case? How do we know?
Because it's the repulsion force?
No, because it's an electromagnetic interaction. You have to get used to that this idea. So the standard model is very abstract model. Okay. That is why we still can describe this the collision of two electrons. One is by force. Can you see? One is by Coulomb force. We still can follow up this force. We can actually measure this force. However, this force is invisible. All right. And these two forces just keep changed. However, in this case, no force. Okay. In this case, no force. No force. But that force is what force has been described by the exchange interaction. Oh, that is abstract. Perhaps I don't want to write this one. The force still there, but we don't use a particle describe it. Can you see? So this is this is a particle model. So this is standard. This is called just bear in mind. This is all called the particle model, right? We have to use a particle. In this case, electron are particle. Okay. By the way, electron is part of lepton. See, How many lepton do you know? Lepton. Have you studied lepton?
Are there electrons, positrons?
That's pair of them. You need to go to next question. So
Anti-electrons?
what means lepton? Lepton. Can you say lepton is also the category of particle, right? Lepton means a light particle. Lepton, which means a light, not too heavy. GHT. Lighter or light particle. You see. Compare with what?
Baryons and mesons.
Oh, meson is a composite, not element. Well, you have learned other things. Okay. Compare with quarks. Okay. Quark is heavier than electron than lepton, right? Did you see meson? Okay.
Yeah.
Meson and baryon. Okay? Baryon, do you see that? Well, that is a composite particle. Meson is made by two quarks, can you see? And so does baryon. Baryon probably made by 3 particle quarks, can you see? So, but before we start, this is called the composite particle. It's not element, can you see? This is a composite particle. See, this is can write list here. So this is called the composite function, composite particle, composite particle. Many particles are described as composite particle because that is why the number of the elements in the standard model is finite. Okay, we will count how many of them. So this composite particle include proton. Are you surprising? Proton is not elements in the standard model. Neutron also is composite particle. It's not element. That's strange.
Yeah.
So basically, if you go to detail, you will learn that proton is made by 2 upper quark and down quark, while neutron is made by 1 up quark and 2 down quarks. You see? So these are these are we call this how so this idea here is similar to the atomic model for chemicals, because every chemical molecule can be considered as made by different atoms. Can you see? So a composite particle, including proton and neutron, can be made by using can be with 1 or more quarks. Does that make sense? But return to the lepton. Lepton is a particle. Lepton is a category as well. Okay. So how many lepton do you know? We know the electron. Yeah.
Anti-electron.
Anti-electron. So we can, if I use the same notation, that would be the anti-electron. Can you see? Let's use this notation. This electron, that would be the anti-electron. Can you see? I use a bar here. Although traditionally we use electron like this and the positron like this, do you agree? So that is electron and positron, but actually they are the antimatter to each other, you see. So let's make another category. So this is matter. Matter is often we say matter, but this category is called antimatters. Can you see? So that is another thing you have to take into account when you study the standard model. Apart from electron, we have the muon, you see. Muon, you have said muon and tauon. Okay, 1, 2, 3. Anything we're missing? Let's check my postcard. Yeah, that is 3. Yeah, that is 3. Okay. So these 3 lepton, they also have corresponding neutrino. All right. So perhaps we will write neutrino. I write down here, neutrino electron, neutrino muon. It's quite different. It's quite, but still, you can count. The total number of these fermion are still finite. All right. That's it. That's Neptune. Can you see? That's Neptune. Can we draw this is you can see this is a table for Neptune. There are 6 of them. All right. There are 6 of them. Of course, if you want to include their antimatter, there will be 12. Can you see? Because similarly, we can build these antimatters. Can you see? You see that tau? You see? You can neutrino, anti-neutrino. Can you see electron? Anti-neutrino, muon. Then that third different neutrino, that is tau. This is tau. Can you see? Can you see that these they are symmetric? They are just antimatters. Can you see? So Neptune, that is Neptune. Do you know what is Neptune now? Neptune is a category. Okay, Neptune is a part of the fermion. Neptune was used or are used to build the matters such as atom. Can you see? After we built a proton and a neutron, can you see here? After we use the quarks to make the neutron and the proton. So this is a proton now, proton model, and this is a neutron model. After building the proton and neutron, we need to pick up electron to build the atoms. Can you see? Not anti-electron, but just electron. Can you see?
Yeah.
So in other words, the hydrogen atom, in terms of the standard model, so this is a hydrogen atom. We got the proton at the center. Can you see the proton, which made by 2 upper quark and down quark, and 1 electron. Can you see? So this is a hydrogen atom. Hydrogen atom. Okay. So that is the only difference, or this is just, so there's not much point to build an atom by using quarks and by using quark, because much easier. Traditionally, what we do, we just call this a proton. Can you see? We just call this a proton, and put this, when we start chemistry, we just call this electron. That's it. All right. So we can count them. We can count them. But if you use a standard model, you have a specified proton is a composite particle made by quarks, right? Okay, your turn. Any question? How much do you know this? Have you studied all the standard model or just the beginning? You mentioned the meson and baryon. Where did you learn this idea? Can you show me the text? Can you show me the textbook? Do you have textbook?
Yeah, I'll see if I can access it.
Okay, I will give you a green light. Yeah, you can. Yeah, you can share your textbook. Because depending on how far you go, all right? There are many strange names in the standard model, but once you know that the basic ideas, everything will become much simpler.
I can show you the syllabus if you want.
Not the syllabus, just textbook. You just, where did you learn this idea or heard of this idea? Did your teacher mention some already?
Yeah.
Do you have digital book? If you have digital book, you can share your digital book. Syllabus doesn't tell much. Okay, you have to look at textbook to see what is exactly discussed.
My textbook isn't loading.
It's loading. Okay.
It's.
Do you use a hard copy or do you use a digital book in the school?
Digital
Use
book.
digital. Yeah, you should be able to open with your computer. Yeah, I can answer your questions based on what you have studied. All right, there are many related issues we can discuss, but you have to make sure we'll discuss the one you are interested in most. You have trouble?
Okay, I got it.
Yeah. Right. Chapter 13, the standard model, yes. So have you read all of that?
We didn't use the textbook much, so no.
Yeah, well, it's very, yeah, I know most teacher don't use textbook, but this, can you see, can you call they call the Gaussian as a force particle, can you see?
Yeah.
They call the force particle. They have reason because the interaction is also, the force is also referred as interaction, can you see? Yeah. Yeah, I think this just it's unfair for students to learn this idea called the gauge boson. They can simply call it boson, all right? Gauge is just abstract word for mathematical purpose, for mathematical constraint purpose, all right? I can tell you this very simple. How about this diagram? Can you tell me what does this diagram tell you? The blue circle.
That everything is a lepton.
Everything is an lepton. What do you mean?
Oh wait, no. So there's leptons and quarks.
No, the gauge boson mediate action between other particles. Actually, you can specify that called, you can for the fermion, all right? Other particle could be called fermion. Okay. That is the reason. That is the key. So in the first, they argue that they try to say the boson contain these 4 particles, right? 1, 2, 3, 4. That graviton is a theoretical, so I think this is I can simplify, or I cannot participate anyway. So this diagram just tell you this blue color, dark blue, will represent that the Popper boson, okay, interactions. So when we say lepton, they just say, for example, electron, okay. Today we know that apart from electron, there are other 5 particles, tau and muon, and their corresponding neutrinos. Okay. Baryon meson is just the particle which made by quarks. Can you see? All of these hadron is called hadron. That is are made by either proton or neutron, or by different number of quarks. Any question? The keyword is a mediate. Can you see? Can you see that is if you understand, you can highlight the keyword is mediate. So what does it mean mediate? It means that the force is not described the proper the force formula. Rather, the force is represented by the proper particle, proper boson. Does that make sense now? Okay.
Yeah.
So the gluon mediate the strong nuclear force. So it's just you know, the alternative way to introduce this abstract idea. Okay. Okay, you can find any new question, any question you can ask. I suggest you read the textbook. Okay, it's better than teachers talk. because afterwards the author must spend a lot of time to edit this chapter, each chapters.
Yeah.
Do you want to select some question to discuss? Quarks. So what is quarks?
Let's just keep going and see how far this gets.
Yes, you can. Yeah, you can select something to read. So this diagram is just to trying to illustrate how the experiment was done. You see, quarks. What are the quarks? How many different type of quarks? That
12.
is the table. 12. Yes.
This doesn't talk about spin.
Well, yeah. They didn't tell. They couldn't tell you everything. Can you go back to your textbook? Disappeared. Your table disappeared.
Yeah.
They should tell you spin, otherwise the quark is incomplete. Just like take the person. If you don't take person's name or height, how can you describe the person?
Yeah.
They probably just talk about their weight, okay, and the other things, okay, age, or but a complete description must include a spin, all right? Where is your textbook? Disappear the textbook
Um,
for some reason. I think next time you will use your textbook, right? You use a highlighter to illustrate or edit some book and you can underline something, highlight something, or make some remark and questions. Then we can discuss that, all right? If you just read now, probably is not very useful. So tell me, what is the standard model you have learned so far?
It is
Why first question, what is standard model? I ask you a question. What is standard model by
a way of organizing particles and like elementary
they call it subatomic particle. We beyond the atom, we got everything. We got electron, proton, neutron. We can use these three elements to build every matters. Okay. Standard model was introduced to describe the subatomic particles generated by observed by at under very high energy. At a very high energy. There is high energy accelerator to observe these new particles, this new subatomic particles. So how do we group? How do we make categories for the standard model? Or how do we put the elements into different category in the standard model? The question is.
They're leptons, which is there are leptons and there are baryons and mesons, and leptons.
No.
Just
Meson,
baryons and mesons are made up of.
Yeah, boson are not that element. I'm asking the question elements. Okay. Proton, neutron, baryon, and meson, they are not basic elements in the standard model.
Baryons and mesons are made up of quarks.
That is not my question. My question is how do we group? How do we put the elements in the standard model into a proper category? That is my question. I didn't ask you how to make a meson on the baryon. Yes. So you have to talk. If you can talk, you can tell. If you can tell people story, then you understand what you're studying.
So if a thing is
how about the student? You see, Students, the school can be divided into primary school, high school, and university. Do you agree? All students. So this, if we consider these students are just elements, so we can put the student into 3 groups. Similarly, in the standard model, how many categories we have used to group different elements in the standard model?
Leptons, baryons, and mesons?
No, no. For some reason, you stick with this baryton every time as if they are the same. They are not the same. As I told you, can we return to the whiteboard here? This is lepton, this is lepton. And you see, we have started out of the idea. Can you see? The standard model is made by elements. All elements can be put into 2 categories. One is the fermion, another is the bosons. Remember your first question, what is a gauge boson? I answer your question now. Can you repeat this story? So what are the groups? How many groups have we used to put these elements in the standard model?
2 gauge. Yes. I mean, gauge bosons mediate the interactions between.
No, boson and fermion. Boson fermion. Next question I will ask you. Once you know the category, that is the first thing, because in the standard model, we only see different elements. Can you see? If you don't use a proper category, it looks very complicated. However, if you prepare 2 baskets, one is called fermion, another called boson, then we can put any element into either of this basket. Does that make sense now? My next question is, what can we do? Why do we introduce boson in the standard model?
Because bosons concern interactions between the particles, and we can use them to explain interactions.
Well, boson is used to describe the each interaction. Okay. Because we know there are 3 basic different interactions apart from gravity. Okay. At the moment, I noticed your textbook says that theoretically they should have the graviton. Graviton is a particle that mediate the gravitational interaction. But unfortunately, there's no such thing. All right. This just a dream. Okay, this is not a dream. Expectation is not a theory anymore at the moment.
Yeah,
it's not a theory even. Okay, probably if you can return to your textbook. If you can ask me question, I can tell you more, because otherwise you can't digest what I'm talking about. You see, this page is a little bit abstract because you have to learn the Fermat diagram. So tell me, what are the leptons? Which group do that? Which category does lepton belong to? Is lepton belong to?
Fermions.
Fermion, yes. Apart from lepton, any other elements in that fermion group?
Baryons and mesons.
No. Why you stick with these 2 composite particles all the time?
Are they not in the?
Well, I'm talking about elements. You see, if I change the subject, if I change the subject slightly, when we start chemistry, all right. When we say, well, so what are the elements for what are the chemical elements? You say water, carbon dioxide, and then tell me carbon dioxide is made by 2 hydrogen, 2 oxygen, and 1 carbon atom. Why? I didn't ask you the carbon or any molecule. I'm asking what are the chemical elements. Do you understand? Similarly, when someone asks you what are the elements in the standard model, you don't have to mention the proton, neutron, meson, baryon, hydron. You don't have to mention this name. Do you understand?
Yeah.
They are composite. They are not elements. When we say element, we are talking about something basic. We cannot divide that element into smaller element. Can you see? So the correct answer to my question is just quarks. Can you see? Apart from lepton. My question is what are other fermions apart from the leptons? The simple answer is the quarks. Can you follow me?
Yeah.
Yes, we don't have to mention the all molecule when they ask you what is the chemical elements. Okay, the chemical elements you say you just pick up in the periodic table, tell them one by one if necessary, but none of them. In periodic table, we are talking about the elements of chemical. You see, with this element, we can build any chemical compound. Okay. Okay. Any other question? Do you want to read that? You prefer don't use your book? Do you want to use your book textbook? Or you can use you can use a PowerPoint of teachers. Can you?
Are color charges important?
Beg your pardon? Color charge important?
Color charges?
Yeah.
Like
color.
We have to color charges of quarks.
Oh yes, you're talking about the property of quarks, all right? And so what is a particle? So how do we describe another issue is how to describe the particle in the element? So how to define or how to define rather how to define element in the standard model. That is question, right? In the standard model. Well, to answer this question, we have to say we have used a table. Okay, we have the just like how to describe the person. We have to put the for example, we have put the name here. Okay, one is the name. For example, up. Can you see? So up quarks is up quarks. Okay, up quarks. Okay, that is the name, and we have used proper notation. Okay. A symbol, can use a symbol. We can use a symbol. We just use U, can you see? After that, we'll talk about electrical charge. Yes, good idea. Electric charge, which is in the unit of electron. And you will notice that it's very strange. There's 2/3, can you see? Positive. It's not integer anymore. And apart from that, we're asked what is a spin. You see, we're talking about spin. You see, they didn't make a spin, but it's important to specify quarks or define the quark elements by mentioning their spin, right? And there are other properties. Okay, there are other properties. For example, they have in the quarks, because for the quark they have the group category. Can you see that is quark can be called as what is category for the quarks? We have the, or where is this anti-quark? I just took example. Okay, another is electron. Can you see? This is something you're familiar with. Electron is also the elements. Okay, the notation for electron is E. How about the electric charge in the unit of electron? Can you see?
It is 1.
No,
-1.
Negative 1. Yeah, negative 1. Yeah. How about spin?
1/2.
Yep, because they are belong to fermion. Can you see? They're fermion. So this just continue. Before we go further, can we just call the electron family, electron? These are the particles we mentioned before, electron neutrino. Okay, neutrino. What is notation? It's nu sub E. Can you see? What is the charge
Yeah.
of the neutrino, by the way? Another thing is the
0.
mass. Yes, that's right. How about spin? Neutrino is part of the Neptune.
1/2.
Yes, 1/2. You see, good idea. See, how about the mass of the neutrino?
0.
Yes, true. Yes, but how about electron for the mass of electron? In terms of
0.
No, if you use this one, no, not if 0. In chem, sometimes we approximate that as 0. We use the MeV divided by C squared. If we use this formula, what is the electron charge?
1.
No, 300, 900, 932. You agree?
Yeah.
And these have proper number. You can find the mass of quark must be larger than this one. Okay. How about the photon? We just jump to the boson now. What is photon? So what is photon's notation? Photon. Symbols, rather. What is symbol for photon?
It is the alpha.
Greek letter. No, Greek letter. Gamma. Gamma.
Yeah, gamma.
Yeah. How about the electric charge of photon?
0.
Yes.
Or
How
was
about
it
the spin?
1?
No.
1/2.
No charge.
Mhm.
Photon have
1/2.
no charge. Photon have no charge. How about the spin? That is the question.
1/2.
No, 1, 0. Double check that. It could be 2 or 1. Can you see? So photons has integers different. How about the mass of photon?
0. There's no
Yes,
mass.
0. Can you see? This is just some example, right? That is how we defined each element in the standard model. Do you understand? We have specified their electrical charge. We have specified their specified the spin and the mass. Okay, so that are the several of the property we can. Of course, apart from that, there are others. Okay, so in order to specify, we have probably you have introduced other ideas. Okay, and for example, if you have the, do you have studied baryon chart? Have you studied baryon and lepton number? You haven't? Have you studied that? No.
Yes, we will study them.
Yeah, we'll study that. So basically, that is how we use this table. Can you see? We can define each element of the elements in the standard model. So that is how we describe the. So remember, when we talk about element, we mean that is a basic particle which can no longer divide into other elements. Okay. So perhaps next time we'll just talk about how to use elements in standard in the element using the elements in the standard model to build a different composite particle. Okay. Today we have mentioned a few. We have mentioned the proton, neutron. Okay. All right. Let's take a break now. Let's save that. Okay, see you next time.
Yeah, I'll see you on Friday.
Oh, Friday. Okay, see you.
Okay,
Goodbye.
thank you.
Welcome.